when I go to the screen that I have the window that I have my slides in, I'm going to, I'm going to have to use down arrow key and so on to go from one slide to another. And that means the focus of the mouse will be in that window and not in the Hangouts window. And I'm asking, that's not a problem, right?
It's not a problem. Right now, we only see your slides window.
All right. Okay, good.
Yeah, it's already on.
Okay.
Yeah, you can start.
Okay, good.
Yep.
So here we are. So I'm really happy that I was invited to talk about this, and thank you for being patient. They said that I could talk about two different topics, which I'm going to do. My package, our package named regression tools, and I'll talk somewhat about the p-value controversy that came out of the ASA statement of a couple of months ago. So here are the two topics. And so regtools, I have it up on GitHub. I haven't put it on CRAN yet, but it's certainly usable. It's been there for a while. I'm continuing to add to it. The description there says various tools for linear, nonlinear, and nonparametric regression. And that's pretty good description, except that it's pretty unconventional, which I'll talk about in a minute. It's meant to accompany my book that I'm working on now, From Linear Models to Machine Learning, Regression and Classification with our examples. I'm about halfway done. In many senses, as I said, both the package and the book take a very non-traditional point of view, which actually is maybe a good thing, because when we get to the p-values, there's nothing more traditional than that, and yet finally the ASA challenged that tradition a little bit, and so maybe it's good to have challenges to tradition in other parts of statistics. So the book, there is a 50% rough draft available on the web. You're very welcome to download it and read through it, and extremely encouraged to give me suggestions. And again, it takes unconventional views. So for example, any regression book, they have the epsilon term, the error term, and they say, let's assume this has a normal distribution. And then many procedures come out of that, T statistics, F statistics, and so on. And I think that's pretty silly, because nothing satisfies that assumption in real life. And so I de-emphasize that. I do use asymptotics, least squares coefficients, estimates of coefficients are in fact asymptotically normal. I use that, but I don't assume that epsilon is normal. Transformations, that's kind of a sacred cow. A lot of people think that transformations are extremely, central to regression and statistics in general. Actually, I think that they distort things, and in fact, there is an FDA policy of some years ago that discourages people from using them, and so do I. So again, that's another example of my book being non-traditional. I have a full chapter on measuring and interpreting factor effects. This is something that I think is really underemphasized in in most books, probably all books, because I don't know why it's underemphasized, but it's such an important area. So, for example, how do you compare several groups with covariates? I have an example there that actually many years ago, when I was a grad student, the first time I did statistical consulting, it was for the Kaiser hospital chain, and we were comparing heart attack patients at their various hospitals, and we wanted to know, are all the hospitals giving the same quality of care? The answer, by the way, turned out to be no, but there was an interesting statistical question there. How do we compare them? And, so there's a lot of stuff in there that I think is just underemphasized in other books, and I have a full chapter. You see a lot. I hope to see a lot of people at the World R Conference at Stanford in end of June. I'm one of the organizers, and I noticed that Max Kuhn will have a tutorial on unbalanced classification problems. I actually disagree with that, and so again, that makes my book a little bit different from everybody else. Max is a great guy, by the way. And then, most importantly, I interweave nonparametric methods with parametric methods, which I think is really important. So, say a little bit more about the package. It's written for the book, but it's usable in general. You don't have to have the book to use the package. As I mentioned, so the book interweaves nonparametric methods with parametric ones, and so the regtools package does that as well. And again, some unusual functions, new ways to do old things, and some ways to do some new things, some of which you'll see in a few minutes. This is a work in progress. I'm adding more and more functions over time. And of course, suggestions would be wonderful. So let's look at multiclass classification. In most books, you see one class. Machine learning books, you'll see multiclass, but I'm not happy with the way they do things either. So I take a different point of view. And so there's this one versus all, or all versus all. Some people have heard of this, maybe some have not. One versus all means you do, let's say, a logistic regression of class one with all the other classes being combined. And you do that one at a time for each class and then predict whichever one seems most likely. All versus all looks at all the pairs, and then you do sort of a voting situation, which class seemed to win the most contests. In my regtools package, I have code for both of them, but both the package and the book argue somewhat in favor of the one versus all. An example, so of course I think a lot of people are familiar with the UC Irvine data repository. One of their sets there is the vertebrate data, and it has three classes of different kinds of problems, diseases with bones. And I use a logistic model in this example. And so here, the first thing I did was I set up training and prediction sets so I could do some evaluation. On the third line of code there, I have a function from my package, OVA, as I mentioned, and then logistic, and it does the training part of the analysis. And I save that in OV out. And then I take another function from my package, OVA log predict, and predict from the training set onto the prediction set, the test set. And it turned out that there's 88% prediction accuracy. That's pretty good. If you use AVA, all versus all, it's a little bit lower, but that may not, that may be sampling variation or something. They're about the same. However, you're doing a lot more computation with AVA. And so at least that example says that maybe OVA is preferred. Letter recognition, another famous example. It's a big favorite in the machine learning crowd. There's an Irvine data set for that one too. But an issue there is that they have about the same number of cases for each letter. And as we all know, Z is very rare in English compared to A. Z is very common in Chinese pinyin, but not in English. So one should account for that. And how are we going to do that? And so we need an adjustment process. In the book, actually, the book does a little bit of derivation. It's not very deep, but there's a little derivation that shows how you could adjust for that, even in the nonparametric case. If you're doing LDA or something, actually the R function for that does do an adjustment if you want for different class probabilities. But I don't know of anywhere where it tells you how to do that in general. So my book derives that, and it's implemented in my functions. So here's an example. And in this case, I'm using k nearest neighbors instead of the logistic model. And what wasn't, well, if you look at the comment, the fourth line of code there's a comment that said, if you just go to this data set and use it straight without worrying about the class probabilities, you get about a 75% successful prediction rate. That's pretty good. But if you actually put in the real class probabilities, then you get about 88%. So big improvement. It's nice. So I have a chapter in the book on model fit assessment. The classical approach is to plot residuals, and in my book, I argue that maybe you can do better than plotting residuals. You can what I do in my package is that I make heavy use of the nonparametric methods. I'm still assessing a parametric model, but I'm using nonparametric methods to help that out. So here's currency data. This is very interesting data. It's one of the economics journals had it, and it's available online. If anybody is interested, they can email me and I'll give them the source. This is back in 1995. So at that time, we didn't have the euro. We still had individual currencies in Europe, like the German mark, the French franc, and the pound. We still have the pound, actually. And then the Japanese yen was in there, and the Canadian dollar. And so what I'm doing here is I am predicting the yen from the Canadian dollar, the mark, the franc, and the pound. And so if you just use a straightforward linear model, what you find is, if you look at the bottom line there, the output of LM, the R-squared value is high. I don't remember the sample size here. I think it was about 5,000. And you can tell it was not that small because the R-squared and adjusted R-squared are almost identical. I couldn't fit this on the slide. I could have done a little bit more to fit it on the slide, but actually it's good that I didn't fit the whole thing. So all the asterisks in the final column don't show up here. In the last column, those are the p-values, but since I don't like p-values anyway, it's not a tragedy that I have lost that last column. Maybe I should have even suppressed the next to last column with the p-values there. But if you really want them, you can see they're all small. Okay, so no surprise that all of these other currencies have some prediction value for the Japanese yen. Okay, now we can do a nonparametric fit. In my package, I have a number of things here that I ought to explain right here. So my package does do nonparametric regression. It uses k nearest neighbors. I have this pre-process idea here. It's the function that basically, when you're doing nearest neighbor regression, you might want to try different numbers of nearest neighbors, and it would be a waste of computation to do the nearest neighbor finding repeatedly for different values of k. So what I have instead is a pre-process function in my package that basically says, in this case, find all of the nearest neighbors up through 150, and then you can use less of them if you want later on.
Can I ask a question?
Yes.
I can ask later. Do you need to scale the data into similar scale because
Right.
k and n?
Yes, there's a lot of details I'm not showing here, but the k nearest neighbor stuff, the functions that I have in my package do allow you to scale, and that's the default. I just haven't shown that here.
Okay, yeah.
Okay. So the second line there, I'm using another function in my package to choose the value of k, the number of nearest neighbors, using cross-validation. And it turned out it was surprisingly small. It was only 5 that gave the best prediction, going up through 30. And so I'm using 5 here. And so let's see, 1, 2, 3, the fourth line of code there, KNNEST, that's where the nearest neighbor regression is actually done. The Ker1 5 was the Japanese yen, and then I have the X data, which is all the other currencies using 5 nearest neighbors. Now here's what's interesting. I then take the correlation, the square of the correlation between the predicted values and the actual values. And that is R squared. I think a lot of people may not realize you can actually compute R squared for anything, for any kind of regression method. You don't have to use linear or whatever, because R squared is the squared correlation between predicted and actual values.
I'm confused there because when I was in graduate school, I learned that R squared for linear model is a percentage of variance explained.
Well, it is, and that's still true. If you take what I just said about the R squared being the squared correlation between predicted and actual value, that's actually mathematically equivalent to saying that you're explaining the percentage of variance. In fact, now that you mentioned that, I might mention that in my book, each chapter has a section at the end called mathematical complements. And the reason I have that is that, you know, some people don't want to see the math, or they may be afraid of it or whatever. And so I have it as an appendix in each chapter, so people can read the main chapter, main part of the chapter without going through the math. But for the people who want the math, then there is a section at the end of each chapter called mathematical complements. And in this particular case, it derives these things of the percentage of variance and so on. It even gets a little bit more abstract than that, with projections and in L2 space and stuff like that a little bit. And there's also a code complement chapter at the end, section at the end of each chapter for people who want to know more about the code. So, for example, in R, we have in S3 classes, for example, we have generic functions. And so in one of the code complements at the end of one of the chapters, I talk about what that means instead of putting it in the regular text. At any rate, 99% R squared, which is really nice. It was only 89% for the linear one. And now we see 99% with the nonparametric. So that's a big improvement. And here's a phrase for non-native speakers of English: we're leaving money on the table.
Oh, no.
Meaning that we could have won more money, actually. And in this case, if we use the linear model, we actually could have done better. There was more, we could do better in prediction. Now, what about the fit? So even for the linear model, so I'm really talking about the fits of the linear model. R squared was about 88 or 89% linear model. That's very good, and you would think that that means the fit is quite good. It turns out not to be true, and let's take a look. So here, what I do is this is another function from my package. I'm showing I'm plotting the linear model predicted values against the nonparametric model predicted values. And if the linear model were really good, then we would have a straight line with 45 degrees. And that's pretty much what we have. But we have some interesting departures from that. If you look at the lower left, there's this funny hook there, which seems odd. And in the middle, there's kind of a tail that goes downward from that 45-degree line. So there are things in here. There's things in these data set, in this data set.
Please mute.
Okay, so slight interruption there. So we have this plot is telling us that we have there's more to this data set than what the linear model is telling us. There's something else interesting going on there, and so we as I said, we see the hook, the lower left. We see the tail near the middle. What do they mean? Well, we have to bring in the domain experts, the people who really know currency and really know currency as of that era, the mid-90s, what was going on. So here is a hint that there's something more in the data that is worth pursuing. We just don't know what it is until we ask the currency people. Okay, now, R, of course, has built-in plots. One of the nice things about generic functions is, whenever I teach people, as the first example I use, in R, you can call plot on almost any kind of object, and usually it's going to give you some meaningful, picture that comes out of it. And here, the fitted values are on the horizontal axis, and I have residuals on the vertical axis. And it's not all that clear. I think the picture here might be a little bit too small. You can see the fitted model. It's a curvy line in the background there. So if in the classical way, residual analysis, what do? We'd like to see that the residuals are about, evenly spaced, evenly distributed above the fitted line and below the fitted line, and regardless of what value of the fitted line we have. Okay, in other words, from left to right, we should always have about the same number of points above the line and below the line. And it's pretty clear that's not going on here. In fact, the tail, the hook that was at the lower left of my picture from my package, you can actually see there in this picture too. I would argue that it's less clear, and so the point that I'm trying to make is that I think that residual analysis is maybe not the best approach. That it might be better to do smoothing, which I'm doing in this other picture. Remember, these are smooth values. I'm using the nonparametric regression to do the smoothing. And I think that the hook is much clearer here at the lower left and the tail in the middle. Whereas in this one, if you know what to look for, you can see them in this picture, but maybe not so clearly.
Wait. Can you repeat your comment?
I can't hear it. Sorry.
Sorry, something wrong there. I heard it equal.
You have one?
I can't. Yeah, the sound is not. You can keep going.
All right. Okay, I will.
Yeah.
Okay, so here there is something called partial residual plots using the CAR package. The CAR package is from John Fox, and I think Sanford Weisberg. It was meant to supplement their regression books. Very nice package. And so they have partial residual plots there. Again, this is a little bit small, but there are 4 currencies here. The ones that I'm using as predictors for the Japanese yen. You can see the one on the top right, that's for the German mark. It's essentially close to a straight line, again with that hook there, but pretty much a straight line. The French franc in the lower left is, again, fairly close to a straight line. There's a little bit of departure. But the Canadian dollar and the pound are just all over the place. And so again, this is suggesting, this is not my function, remember, it's from the car package. It's suggesting that maybe there are other issues going on with the Canadian dollar and the English pound. So, but let's focus on the German mark, which is the upper right. So again, that is mostly close to the 45-degree line. It's cleaner than the other graphs, so it's it might imply that maybe there are not any special variables that we don't know about that are lurking behind with the German mark. But actually, that's not true. So if you use my plot from my package, regtools, the function name is nonpar versus xplot. So these are plotting against each variable, each predictor variable. That's why it says next plot, next plot, next plot. This was the fourth one. This user keeps hitting enter and it gets different pictures coming out. So this is for the mark. And there's huge departure here from a straight line, that there's all kinds of there's all kinds of points that are above that straight line. So which was not apparent in the upper right picture there. So again, I think that there is a good argument for doing smoothing, and it'll allow you to probe more deeply. But again, we need the domain experts to tell us interpret that picture, and all we can do is say, here's a tool for you, and then the domain experts have to analyze with it. Okay, let's go to p-values, and I have been saying for years that people shouldn't do p-values. It's kind of interesting. Some of you may know that the current ASA president is Jessica Utz. She used to be my colleague at UC Davis. And I'm sure she remembers me ranting and raving about p-values and hypothesis tests long, long ago. And I'm not the only one. The problems are well known. There's a book called The Cult of Significance, a whole book on the subject, actually, The Cult of Significance. And on page 2, I think there's a list of famous people who were critical of hypothesis testing, significance testing, including Einstein and Richard Feynman. So what are the problems? If you look at the two sub-bullets, they're addressing an irrelevant question. So let me give an example that's not on the slide here. Since this is an election year and we see all of these polls before the primary elections, so suppose that you are working for Bernie Sanders and you are his pollster, and you get a small poll, and the small poll in some state it would have to be a very small poll for these numbers to work. But let's suppose that in that small poll, we estimate that let's say we form a confidence interval for the proportion of voters that will vote for Bernie Sanders. And suppose that interval comes out, let's say 48% to 62%. So we're saying we're 95% sure that the true proportion that are going to vote for Bernie are between 48% and 62%. As everybody knows, you can use a confidence interval to do a hypothesis test. And so if you go by books, they would say, oh, well, the hypothesis is not rejected. And the pollster for Bernie Sanders would have to go to Bernie and say, unfortunately, you and Hillary have no significant difference in this particular state. And that would be, I think that would be very misleading, and it would be unfortunate. In fact, I would say that um, that pollster that Bernie hired ought to be fired because I think Bernie would like to know that the confidence interval is 48% to 62%. It doesn't say he's definitely going to win, but it wouldn't say that anyway because it's only a sample and people change their minds and so on. But 48% to 62%, most of that interval is in territory very favorable to Bernie Sanders, and I think he would want to know that. So not only that, it's suppose on the other hand the confidence interval were 50.2% to 50.8%. The hypothesis testing people would say, Bernie, you have a significantly higher percentage of supporters than Hillary does. And that would be really, really misleading because 50.2% and 50.8% are still very close to 50%. So, in two directions, you can have very misleading results if you use the hypothesis test. And if you look at that first sub-bullet there, it says that the tests are addressing an irrelevant question to begin with. Because, whatever the percentage that are going to vote for Bernie is, it is not 50.000000 with infinitely many zeros percent. It's something, it may be very close to 50%, but it is not exactly 0.500000 with infinitely many zeros. We know that. And yet the hypothesis test is asking that question. It's asking whether the percentage that plan to vote for him is exactly 50% to infinitely many decimal places. That's ridiculous. We know a priori that H naught, the null hypothesis, is false here. So why are we asking a question that we know a priori is false? It just doesn't make sense. I think as for those of us who teach statistics, and I do actually, even though I'm in a computer science department, we have some courses in statistics as specifically for CS students, and so I do teach this, even though I haven't been in the stat department for a long time. And I would be embarrassed to try to tell students that they should accept this because it's so silly. They should not have any faith in me at all if I try to convince them to use this. And yet that's what's being taught all over the world in every statistics class, that you should do this. So that's why many of us have been saying for many years that we shouldn't be doing this. Now,
well, but from the practical standpoint, like I'm working in marketing, sometimes we want to know if a marketing campaign or a promotion program will work, will increase the conversion rate. We need to have a way to measure that.
yes, of course.
Can help or cannot help then. Since
so that's the point. Is it helpful or is it not helpful? And if that marketing program increases sales by 10 cents, then it's not worth it. It's not helpful. Okay, you want it to increase sales by $10,000 or $10 million. You don't want it to increase sales by 10 cents.
Yep.
And the hypothesis test is not telling you that. Okay, it's not telling you how much it is increasing sales, or maybe it's decreasing sales also. The key point is the test isn't telling you the size of the effect. And so in my example with Bernie, I said, suppose the confidence interval says 50.2% to 50.8%. That still is very, very close to 50%. It's not, in that scenario, it would not be very encouraging for the Bernie Sanders camp. So the problem is that whenever I talk about this kind of stuff, the problems with p-values, and people think, well, oh, you don't want to make a decision. They think that I don't want to make a decision. Of course you have to make a decision. You have to decide if that marketing campaign is going to be helpful. And I mean, that was your word. Is it going to be helpful? And I agree. You do have to make that decision, but you want to make an informed decision. Helpful means, it doesn't mean increasing sales by 10 cents. Okay.
What about the conversion rate drop from 50 to 60? And if the p-value is not, what if 10% is what we want, and we want to know that 10% is not from random error? How
Well,
can we make sure that 10% is real?
well, first of all, it's not quite true, because if it's 9.9%, you're probably still happy. Okay, so again, the null hypothesis here, you're going to say the null hypothesis is that there's an increase of 10% versus more than that. That's unrealistic too, because you're probably happy with 9.9%. But the real answer to your question is, again, is a very simple answer. You form a confidence interval. You just don't use the confidence interval as a means of doing hypothesis testing. You really use it. In the Bernie Sanders example, if the confidence interval is 48% to 62% in favor of him, then that's something that's immediately meaningful to Bernie Sanders. In your marketing campaign, if you form a confidence interval for the percentage increase in sales, and it comes out 9.8% to 13.2%, then the marketing people will be thrilled, because and they're not going to be bothered by the fact that the lower bound is 9.8. It's still close enough to 10 for their purposes, and they'll see that it could be as much as 13. So this is much more informative for them.
So it's what about weird?
Is there another question coming?
Yeah, I want to ask. It's actually a similar thing. You just report confidence interval, then it's also parametric still.
No. Well, you can
calculate the variance and.
Well, you can always calculate a variance. I mean, it depends on what you mean by parametric. I can if I'm doing nonparametric regression, and I want to know, suppose in the currency example, I say, okay, there's a given value of Canadian dollar, pound, mark, franc, and I want to know what is the regression value for the yen at that particular value of the other currencies. I can form a confidence interval for that. I mean, when parametric model, when I use the term parametric model, I'm saying, if I'm going to predict weight from height, people's weight, human weight from human height, the linear model says that the regression function of weight against height is a straight line. The nonparametric model says we don't know what the form is. We're not going to make that restrictive assumption that it's a straight line. So we call it nonparametric, but that doesn't mean that there aren't variances of various quantities, and so you can still form confidence intervals.
For resampling?
Well, you have sampling anyway, but are you talking about maybe resampling?
How to make confidence interval? What's the mechanism behind the confidence interval if you don't have an assumption for?
Well, the point is that you have, if you look, here's a rough way to do it in the nearest neighbor case. Again, let's just, I always like to use the predicting human weight from human height as my example, because everybody understands immediately. So let's say I want to know, I'm interested in the mean weight of all people that are 70 inches tall. And I have a sample of 2,000 people. Okay, then I can look at the people in my sample who are, let's say I take the 50 closest people to 70 inches tall, and then I can take the average of their weights, and I can find the standard deviation of their weights, and roughly that will give me a confidence interval. If I take the mean of their weights and plus or minus 1.96 times the standard deviation of their weights over 50, then I can get a confidence interval for the mean weight of all people 70 inches tall.
Mm-hmm.
Now, there's a little bit more to it because of the fact that there's a bias term, but the point is it's still doable.
Okay.
Okay.
Yep. Thank you.
Okay. Another interesting thing about this before I go on is, I used to do expert witness work. I don't do it anymore in courtrooms, okay, in legal cases. And I don't do it anymore because it's just too time consuming. But it's really funny. If you try to explain a p-value to a lawyer, it's impossible. It's really impossible to explain a p-value to them. But if you explain a confidence interval to them, they immediately understand. And one reason that they do is that they're used to seeing on TV all these election polls, because the election polls all talk about the margin of error. And the margin of error is just the radius of the confidence interval. They don't tell you that on TV, but that's what it is. And so if you talk to a lawyer about a confidence interval, they understand right away. If you talk about p-values, you can explain for hours and they're still never going to understand. By the way, I might mention there's a very good write-up. It's about 90 pages long. But for those of you who do consulting and want to explain basic statistics to people who don't know much, all those lawyers, they all had a stat course when they were in college, but they all got C's. And so, they hate it. And so there's a very good document. It's called Reference Guide to Statistics. It's by two authors. One is David Friedman, who some of you know his research or his book. He was at UC Berkeley. He passed away, sadly. And the other one, I think his last name is Brown. I don't remember, but he's a law professor. And the Supreme Court actually commissioned the two of them to write this. It's a very good document, Reference Guide to Statistics. Now, in my blog, I have a blog, matloff.wordpress.com, about statistics in R. And when the ASA came out with their statement about p-values, it caused quite a stir. Let me go to the next bullet. So the ASA decided to address the issue because there are a lot of problems. I'm not sure how many people are aware of this, but there was about 3 or 4 years ago, I think 2012, may have been even earlier than that, maybe 2011, but there's this guy named John Ioannidis who is now at Stanford, and he wrote an article. It was in Nature or Science, I don't remember, but it caused a huge commotion because he was saying, science really has a problem of lack of replicability. You see a study that says one thing and then somebody else tries it out in another lab, and it doesn't work. It doesn't replicate. And part of the problem is statistical. Part of it is other things because different labs have subtle differences between them. But a lot of it is statistical. A lot of it is multiple inference, trying to do many tests or intervals at once, and then you kind of choose the ones you like, which of course you shouldn't do. And so this caused a big stir, and it caused, I think, a lot of soul searching in the ASA. And then also another factor is that a lot of people in the ASA are concerned that they're losing ground to computer science. And I actually wrote a blog on that, and later the ASA asked me to put it into Amstat News, since I have a foot in both camps in CS and statistics. And I think there's just a lot of concern that among people in the ASA that they have to be more relevant, and because statistics is important, and that should be recognized. So I think one of the outcomes of that was they appointed this committee to look at p-values. Now, here's another famous saying: a camel designed by a committee, it's not a very good camel. If a bunch of committee people design it because they're not they can't agree. And apparently in the in the committee that was appointed by the ASA to study the p-value issue, there was, I think there was, a lot of disagreement. Um, if any of you are not familiar with Deborah Mayo's work, she's a philosophy professor at Virginia Tech. I think she was on the committee, and she's really great. She has a great blog. It's an anti-Bayesian blog. It's really good. And she's a philosophy professor, remember. And I think she was on the committee, and I think she actually likes p-values. And she was probably not alone. So when you put this kind of committee together, you're not going to get a really, really strong response. But I think the fact that ASA made this, appointed the committee, and that they did agree on a lot of things, and they issued this report, I think that that's just remarkable. The ASA has been around for 150 years, actually, and it's just a remarkable thing for such an old organization to do. So I was just really pleased by that. There's some disagreement even by people who read the report. I claim that the report really says, I think the report, in my view, the report comes very close to saying don't use p-values at all. There's some people who take issue with my opinion on that, and there was quite a discussion among readers in my blog when I discussed this. But I think if you read the report, you'll see that although the phrasing is a little cautious, they don't have any instance there where they recommend using p-values, and I think that's very telling. I have an example here, the movinglens data. Some of you may know about that. This is for recommender systems, and you have all these movies, and you have different users who are rating some of the movies, and we'd like to, if I'm one of the users and there's a movie I haven't seen and I'm considering watching it, I want to know what, I want to sort of predict ahead of time whether I might like it. So recommender systems are supposed to help me do that. And this shows you some of the data. Of course, I didn't show reading in the data and all that. I have age and gender there, occupation, zip code, which, is very useful, but you'd have to use it in a more subtle way than I am here. And then the average rating. So the ratings here, movies are 1 to 5. 5 is best. And so the user number 1 was age 24. I think 0 was female. She was a technician and living in a certain zip code. And of all the movies that she rated, the average rating she gave was 3.61. The second person was of age 53, and that person was a little bit more generous in her ratings and gave an average of 3.7. Remember, these are not for the same movies. They may not have seen the same movies at all. But let's do a regression here, and this is just a simple-minded approach to the problem. It's certainly not the way most recommender systems work. But let's take a look and predict the average rating from age and gender and see what happens. So there you see the output, and somehow the stars got into the slides here, and so you see age is highly significant, 2 asterisks. And yet, if you look at the actual estimate as 0.003, think about what that means, because we're talking about ratings on a scale of 1 to 5, movie ratings of 1 to 5. And so if I am 10 years older than somebody else, that means that I take 10 times 0.0033, I get 0.003. That's tiny. The 10-year difference in age made almost no difference at all in the mean rating that I give versus somebody 10 years younger than me. So, and then the R squared was also very tiny. So, what does this tell us? It tells us age is not a good predictor of movie ratings at all. And yet, if we were to take, if we were to do what we were taught in school, um, then, in statistics courses, we would look at those two asterisks, the two stars, we'd look at the p-value, 0.004, really small, and we'd say, oh, age has a highly significant impact on movie ratings. And it's just not true. It would be egregiously misleading. Okay. So age effect is what people call highly significant, and yet it's highly unimportant. And when I teach this, I like to have fun in class. So I like to joke around with my students. And I have a number of students who are not native speakers of English, and I say, who's a volunteer who's not a native speaker of English? And somebody always volunteers, and I ask them, are the two English words significant and important? Are they the same? Are they synonymous? And the person always waits for 2 or 3 seconds and wonders if it's a trick question. And then they say, yes, they're synonymous. And I say, yes, they are. Of course they're synonymous. Of course they mean the same thing. But of course, that's why this is so misleading, that it's traditional to say, we look at those two stars by age, and we say age has a significant impact on rating, meaning it's important, and of course that's not true in the least. Okay. So clearly there's a need to change. Will things change? I don't think so. The ASA announcement was really, really good. It caused a lot of discussion. But people like simple, crisp answers. Will the marketing campaign help or not? And if they are told the marketing campaign has an impact significantly greater than 10%, then people will be happy. But they may be misled, because if it's only 10.001%, maybe that isn't what they were hoping for. They don't like hedging. They don't like a confidence interval. They really don't like that. They don't like, well, the effect of the marketing campaign might be 9.8% up through 13.2%. They don't like that. They just want to say yes or no. Is it going to work or not? And that's not in their best interest. But they like simple answers. And so that is a big barrier to having people change here. I like to use the metaphor of bedtime stories for kids. People who teach statistics, it's a story for them when they talk about p-values and they talk about the student t test and things like this, or even in regression when they talk about epsilon being normally distributed and they talk about using a square root transformation for Poisson data and stuff like that. These are like telling the story of Goldilocks and the Three Bears to the kids. They like doing it. They've been doing it for years, and they like telling this story. And for that reason, they don't want to change. So there's another big obstacle. And so I will conclude my presentation with one more bullet. Will the ASA statement have any effect? I think that is a big question. And so that is the last slide. Thank you.
I think another reason people can't change is sometimes we need a lot of comparison. If we have hundreds of comparison, how can we examine confidence interval one by one?
Well, that's actually very, I think that's a very legitimate question. Of course, there's the deeper question of the multiple inference issue that I mentioned before, because whether you're doing testing or intervals, either way, when you're doing many, many of them, they begin to lose, their accuracy, right? They're not simultaneously accurate. So that's a first issue. But, there are other things you can do. You can say, well, I'll look at ones where the point estimate is above a certain level, you can do things like that. If you're doing if you're looking at many, many means, for example, they probably have about the same standard errors. And so you can say, well, let me look at the ones that are the biggest, for example, that, if you're looking at different, um, this marketing campaign on many different products, you might say, well, let me look at the one that's the biggest. Again, if you're doing that, that's very dangerous, whether it's testing or intervals, because the one, the one that's the biggest may be there by sampling variation after you look at so many different products. But, again, that's you're bringing up what I think is the central issue, that the alternatives to testing
Yeah.
are messy. There's no good formula for them. You have to do it. You have to look at the situation and come up with a good method.
So does that mean we have to admit that statistic has the limit? So it's just the limit of statistic. It's not as useful as we thought before.
Well, I hope that we thought before that we already knew it had limits.
Before, I think people still use it quite extensively.
Well, just the issue that I've mentioned twice now, the multiple inference problem, that right away is a key issue. If somebody comes through a few statistics classes and that has not been emphasized, then there's really a problem with those classes. That you can't, when you do so many comparisons, whether testing or confidence intervals, when you do so many, some of them are going to look very interesting just by accident.
Yeah.
So I mean, just simple Bonferroni inequality should be taught even in a very basic statistics course, just to dramatize the problem for people.
For the nonparametric method, do you think, based on my experience, sometimes those complicated methods won't work well for prediction because they tend to overfit the data, training data, especially when you want to predict for the next year. Usually,
Right.
not good to use method like random forest to extents.
Right. The overfitting is a problem both for parametric and non-parametric methods, for any of them. So it's k-nearest neighbor, random forests, neural networks, linear models, logistic models, whatever you want. It's a problem for any of them. There's also the problem of the so-called curse of dimensionality, because you mentioned before we started that your data set has 570 variables. So there's that issue too. Again, no easy answers. But to answer your original question about non-parametric, actually, I prefer parametric. For classification, I really do prefer the logistic model. And there have been a lot of comparisons made. Unfortunately, most of the comparisons I think have been pretty biased, and they haven't been very good. But there's one comparison I saw a number of years ago that I thought was very good on classifying, and it had all the models I just mentioned plus a lot more. And the two, and they used cross-validation so that they were predicting the next year, as you said. And the two winners in that, interestingly, one was SVM, support vector machines, which I regard as semi-parametric, not non-parametric, and logistic regression. That was the other one, and they did about as well. But not only that, actually, I claim that the logistic model would have done better than support vector machines if they had allowed interaction terms. And that's very important because SVM implicitly has interaction terms because you run the data through this transformation that basically makes it, it just destroys the linearity of everything. And so basically you're allowing for interaction terms now. And so in that comparison I just mentioned, SVM actually had an unfair advantage over logistic because logistic, they were just doing straight, without interactions. In fact, in my book, the letter recognition example I just mentioned, that actually was an issue. If you go, it's in that 50% draft on the web. If you go over there, you'll see that even adding a few interaction terms really helped a lot. And so it basically is saying that there was sort of a bad model to begin with, because with something like image stuff, you can't expect monotonic relationships there. With, for example, with the letters. So I think so. In other words, let's go back to your original question about using nonparametric methods. I use them just now in my talk. I use them in my book mainly as a way to do the diagnostics, to do the model fit assessment, and things like that. With the currency data, the nonparametrics showed us that the linear was not enough, that there's more going on in that data set. That was useful. But that doesn't mean I think we should use nonparametrics there. It just means we should elaborate on that linear model. And so I'm very much in favor of parametric models.
And for another is about variables, like SVM has variable selection function in it. And random forest, it actually won't be affected by collinearity.
Well,
free model won't be too.
Yeah, I mean, we're talking about very large data sets. When we're talking, I mean, SVM and random forests they're usually used on very large data sets. And in that case, the multicollinearity is not really a problem. I mean, multicollinearity is a problem because it causes standard errors of coefficients to be large.
Yeah.
But if your data set is very large, you're going to have small standard errors anyway. It's not an issue.
Like for my data set, do you think that's large enough, or?
Oh yeah. Well, the problem is when you say large.
200,000 variable observations.
Well, you said you had 2 million observations, but you also have 570 variables, and then so what's large for n in a way depends on how large p is also.
And from practical point of view, we need to identify which variable we call drivers, because for marketing point, we can't focus on every one of them.
Yeah.
We want to know what's the most important thing we should focus on, and how going to be the impact.
Right. I have not gotten to that chapter in my book yet. I'm writing that probably in the next few weeks.
Oh, you have that topic as well?
Yeah. That's a big topic. That's a very central topic. Model selection, including variable selection.
Now, the method I found that's most useful is lasso. I really like lasso, the penalty-related method.
Mm-hmm. Well, I think lasso is very interesting. But if you look at my blog, I had a blog posting. Maybe 6 or 8 months ago, maybe more, on lasso, and showed that it was choosing a lot of wrong variables.
Okay.
Okay. There's a famous data set which I think I cite in my book also, by people at the Wharton School. Okay. Where it was on stock data, I believe, and what they did was they added a lot of fake predictor variables to it, and they just used significance testing to choose which variables to use. And of course, what they found was all of their fake predictor variables were chosen as significant, and I think that's a big warning there.
That's for linear. That's for continuous variable, not for categorical.
It doesn't matter. It doesn't matter.
Categorical situation for us, at least the prediction accuracy is very good.
Well, that may well be true. Here's an important point that I make throughout my book. You really have to identify early on whether your goal is prediction or description.
We have both, so we want both. We want to be able to predict and also give the most important drivers.
But what I'm saying is that if you only want prediction, then you can have a poor model and still predict well, okay? But if you really want to know, if you want to understand what's going on, then you need the description. And throwing out variables because they're collinear is very dangerous if you do that, because then you have all these problems like Simpson's paradox. But to go back, you said something else a minute ago. Oh yeah, lassos. I didn't finish on that. So the point is, on my blog post.
Back to that one. Sorry.
Well, that's all right. So in my blog post, I did the same thing as what the Wharton School did, and I added a lot of fake predictor variables, and sure enough, the lasso chose some of them. There's no easy answer. You can't just say, well, lasso is going to solve all the problems. Even the people who developed lasso would not make that claim.
Mm-hmm. If the model can predict well, how can you tell the variable are not the right one?
Well, that's my point. It can predict well without the variables. You can have a Simpson's paradox kind of situation where you're predicting z from x and y, and with x and y in the prediction equation, let's just say linear, then the coefficients of x and y will be, maybe very different from whether you have just x. And yet maybe x already is a strong predictor of z. So, that kind of scenario shows that having a good predictor does not necessarily say that you're gaining good insight into the underlying process.
And we have no way to know that. It could happen, but we can't detect it.
That's right. Well, if you have a variable, you can detect it by adding it in, but there may be variables that you don't have data on. And of course, you're right there that you don't know. You don't know that if, maybe that missing variable would have really changed things. That's always a problem. Yet another limitation of statistics.
So we just have to leave it from in our situation. You have to believe the variable picked out. That's the only information you can have. You don't know.
But you can be careful in picking those variables among the ones you have. That's what I'm saying. The other point is, if you are doing description, then the lasso is really, now it's getting very shaky, because you're shrinking the coefficients, and you may be shrinking them in non-uniform ways. And so if you're saying, as you did, you want to see which of the predictors is most important, if you're going to just look at the coefficients to do that, and these coefficients have been shrunken, then again, things are becoming very shaky.
I don't get that. What if they are all in the same scale? You centralize and scale them.
Well, no, that's fine. You can scale everything, but the point is that the lasso or ridge regression, either one of them, lasso came from ridge regression, right?
Yeah.
And so, with ridge regression, it's a little clearer that you can see for sure that that the ridge regression is shrinking the coefficients. Whether the data was scaled to begin with doesn't really matter. Whatever you have, even after scaling, you're still shrinking those coefficients. When you use ridge regression, you're also doing that with lasso. And lasso also came from James Stein estimators. You go to statistical theory. If the famous theorem says if you want to estimate a vector mean, in squared error, with squared error penalty, then do I have is it greater than 3 or just greater than or equal to 3? I don't remember. I think it's in 2 or more dimensions, the mean is the best estimator, but in 3 or more dimensions, 2 or fewer dimensions, the mean is best. Sample mean is the best for the population mean, but in 3 or more dimensions, the sample mean is not the best estimator, and you have to use a shrinkage factor to get the best for in L2 error measure. So again, back to the shrinkage, and so the lasso was motivated also by James Stein estimators. And so basically in Lasso, you're saying, I'm going to shrink my coefficients. That's something I really don't want to do, but I'm doing it in hope of getting better prediction because I'm reducing variance of the coefficients and so on. Okay, but there's no free lunch. There's no easy answer. And so again, if you're doing description, I really would not recommend the Lasso. If you're doing prediction, you may do quite well.
Yeah, Lasso so far is good for prediction.
Mm.
And it also shrinks the parameter to 0, Lasso.
Well, that's what I'm saying.
Yeah, it's variable selection. Yeah, as you said.
Well, I mean, okay. So if you use right, so if you instead of Lasso, if you use elastic net, then they don't come out 0. But the whole point of Lasso is it's motivated by shrinking the vector parameters.
Then what gonna be a good way to do parameter selection? I compare, like I use Lasso and I also use SVM and random forest, and I compare like what the most important variable identified by random forest and what are those identified by Lasso. That's all I'm doing right now. I don't know how to do it. And I pick the best model with the best precision, and for description, I will try to compare different models.
Did random forest and Lasso give you the same variables?
Very similar. Top one are very similar.
Okay. Okay. Yeah.
Mm-hmm. What's your recommendation for parameter selection?
Well, I really don't have one. I mean, all I can do is I say there's no good answer.
Okay.
You can try various things. You can try Lasso if you want. You can try cross-validation with a sort of a nested set of predictor variables. Otherwise, you can't take all possible subsets, but if you have a lot of them, but you can say a nested subset of variables, and in a very minimal way, you can just look at adjusted R-squared for each one if you want. If you want to look at it that way, there are a lot of things you can do. None of them is an easy answer, though. I assume you're doing all this with cross-validation, right?
Yeah, I use cross-validation.
And then with Lasso, are you choosing the shrinkage parameter with cross-validation?
Yeah, choose the Q-mean parameter, and then my tax set is next year's data. So
yeah. Okay. Yeah.
Data tax. Yeah.
Right. So again, even there, if you're going to say, well, take the tuning parameter value that minimizes the prediction error, again, you have the multiple inference problem there. Okay, that you may by accident find there by random accident there may be a tuning parameter value that actually is not very good.
Yeah.
Same thing for what I did just now with nearest neighbors. I used cross-validation to look at various values of k for k nearest neighbors. By accident, one of those values of k could look very good, but you still have that random problem. There's no easy answer to this.
Okay. All right, we just have to live with it.
Yes.
Yeah, thank you very much.
All right.
Do you change the link for your book if you update the book?
No, I think I'll leave the draft there.
Okay.
People ignore the real book when it comes out.
Oh, okay. So we have no way to access to updated book.
Yeah.
Okay. Can you send the link for your slides today?
Yes. Okay.
Okay, and I can collect question later. They can leave question on the event page or under the meetup page if they watch video later. I think they will watch video later.
Yeah, I'm looking forward to seeing them.
Yeah, okay. And let them send email to you or leave message under your blog.
Okay, good.
Yeah, thank you very much.
All right, thank you. I enjoyed it.
Yeah.
Okay, good night.
Good night.